sort of gives you, then just had F left, and that is why F had the last two pre-visit and post-visit numbers, right? So F was 23, and then that was the time of first discovery and also the last discovery, because that F was done, because F did not. So for every node, we have these two numbers, right? One is a pre-visit number and one is a post-visit number. That gives you an idea about the size of the subgraph, this interval for pre-U and post-U. This gives you an idea about the size of the graph, that is the subgraph after U, right? So that is connected only to U. And similarly for V as well. But there are also other properties that we can infer from these post-visit and pre-visit numbers. We'll come to that. But now let's look at another example. That is the depth first search algorithm. We talked about depth first search algorithms when we were talking about undirected graphs. But a graph can also have directed edges. So a directed edge of a graph essentially means that, let's come back to that example. Here we were going through E to J, J to I, or we could have also gone from E to I and I to J. Think of these connections as bidirectional connections where we can go either from I to J or J to I. Doesn't really matter. But a directed graph only allows traversal through a particular location. So when I say A and B are connected with this particular edge, we can only go from A to B, but we cannot go from B to A. That is not possible, right? So this is a directed edge. And so this is an example of a directed graph where we would have connected edges, where we would have arrows depicting which direction to go. So if I come back to that previous example here, so let's say that I put some directions here. I'm sorry for the bad diagram. Ooh, this is going to be tricky. What can I do? Parvez, do you mean that what would be a real world scenario for a directed graph? So a directed graph is really, really essential when we are talking about causalities. So you are imagining a graph where we are saying that it looks like sort of a maze where we can travel through. But that is not in the real world Euclidean space, we can say that if I can go from here to here, I can also come back from there. But you can imagine that there are certain scenarios where we can only travel one way, right? We are not allowed to travel another way. So yes, a one-way street is a very nice example that can be represented as a directed graph. But if you think about hardware, right? So circuit chips, there is something called a diode that only allows passing or allows current from one direction, but it does not allow electricity in the other direction. Now, if you wanted to represent that particular circuit as a graph, you would need directed edges, right? So there are many real world examples for directed graphs. You can look them up, but I think I have, let's see. So this is an example of a directed graph. I'll come to this. Let's see. Okay, so yes, as I was saying, you can have some real world examples where directed graphs are obvious, but you can also use them to model things like causalities, where you say that a particular vertex affects something of a particular area later. Right, so that would have an edge from one vertex to the other, but not the other way around. So you can imagine that if it was really hot today, the sprinklers came on, but it wasn't. That is a causality, but right, that could be represented as a directed graph from the sun to the sprinklers. But it can't be the other way around. That says that the sprinklers came on, and that is why it is really hot. Right. So those are what we call causalities. Then we can also represent hierarchies and things like that as well. We'll talk about those later. So let's see. So let's say that we have this particular graph, and now again we are going to think about the same thing, right? How do we represent this particular graph? But this becomes easy, right? Because here we see one is connected to 2 and one is connected to 3. Now in this case, one is not connected to 4 anymore. So that is the same representation as we did with directed edges, but now we just have sorry, for undirected edges, but now we just have to have fewer edges because we have one-way edges. So 2 is only connected to 4, so this becomes this. 3 is connected to nothing, so 3 is null. And 4 is connected to 1. Right. So this would be your new adjacency list for a directed, for the same directed, undirected graph, but now with directed edges. Similarly, we can also change things in this particular adjacency matrix here to show that one edge is a directed one or not. Now, before I change this particular matrix here, I want you guys to note one thing, that this edge is an exact mirror of the other, right? We have 1 for 2, 3, 4, and then we have this particular one node here. And then in the opposite end here, we have 1, 1, 1, and this one. So it is exactly the mirror side of the other. Dheeraj, what do you mean plus 6? Okay. So yes, it's a diagonal matrix, exactly. Okay, so this was a diagonal matrix because this was an undirected graph. But every time we are representing an adjacency matrix, a graph using an adjacency matrix, and the graph is an undirected graph, we would always have this sort of a diagonal matrix. Now, in case of directed edges, on the other hand, our graph does not stay there. Now, a graph for basically in this case, we have 1 from, so 2 to 3 from 1. So we remove this particular one and this becomes 0. Then we have from 2, it only is connected to 4. So that goes out and this becomes 0. 3 isn't connected to anything. So this becomes a 0. 3 has an entire row of zeros. This is what we call a sink vertex. We'll come to this later. But a sink vertex is essentially some vertex where no edges go out of it, but some edges can come into it, but nothing goes out, like a kitchen sink, right? Okay, and finally 4 only has a connection to 1. So this no longer is a diagonal matrix, but in essence, this now represents your directed graph. So again, we can use DFS to explore our directed graph as well, because given any graph, we can still use DFS to explore that particular graph. And we can also find out the pre-visit and the post-visit numbers, and that would come really handy when we are talking about directed graphs, but in essence, in more detail later, but okay. So does everyone understand the difference between a directed graph and an undirected graph, and what DFS is and how we can explore these things or these graphs? Any questions till now?
The DFS is going to just, it's basically just going to not have to explore as often, right?
Yes, it basically would not have to explore as often, that is correct. But there is a certain difficulty with directed graphs. Remember that our DFS algorithm would search, well, not a DFS algorithm per se. Well, DFS algorithm doesn't have that issue. So let's say that you're traversing a directed graph. Well, I was thinking of could you come back to your question again?
Yep.
Hello?
Yeah.
Could you repeat your question again? I was thinking of you talking about cyclic graphs. Okay.
Oh, I was saying that you don't have to call explore as often because you're not
Yes.
You only ever traverse a edge once, correct?
Yes, you only ever traverse an edge once, and in this scenario you're still doing that, but now it basically means that the next check that we, so the complexity for this is still going to be v plus e. But okay, so imagine that we covered D, and then we had this particular child node A, and we also covered that. But from A, we are only going to look at B, C, and F. We are not going to look at D as, and not consider that as a child. So it is going to, as you said, it will cover, it will look at fewer edges. but it is already explored. That's a different thing. But even if D was not explored, in this particular scenario, let's say we start with A, then we are going to look at B, C, and F, and we are not going to consider D, because although that's an edge that is coming into it. Is that
Right.
what you're?
Yeah. So basically, the time complexity of doing a undirected graph would be V plus 2 times E, but in this case, it would just be V plus E, correct?
Yes.
So you're only ever traversing an edge once?
Yes. Yes. It is going to be V plus E, because once we get there, it is not needed to check for that, because that is not a possibility. Yes, you're right. That would be V plus 2E, and this would be V plus E. Exactly. Good observation. Does that make sense what you just said to all of you? Why the time complexity, although it is V plus 2E, it essentially becomes V plus E, but why for an undirected graph, the time complexity for performing DFS on an undirected graph is sort of V plus 2E, because, let me come back to that, because every edge is examined exactly twice, once from X and once from Y. But in case of a directed graph, once we go from A to C, we do not need to check the vertex A again, because there cannot be an edge from C to A. I mean, there can be, but in this scenario, there isn't. Right? But remember that since we have, I mean, it is going to reduce the number of edges, and also potentially, well, you're right. Okay. Okay, so now before we, I'm going to end at this particular slide here. So before we end, let's talk about certain type of edges. So edges, all edges are the same, but once we discover a particular graph through the set of edge, through a set of through an algorithm such as DFS, we are basically choosing a set of edges to represent what that graph has explored, right? So let's look at this example. So in this case, we can see that we started off from A, we looked at B and E, those are all valid edges because we actually tried to explore B, and then we tried to explore E, and we use the edge from E to I to go here, and then explore I, from I explored J, and once we are done, we are not going to explore this particular edge anymore, right? So this is an edge that your DFS algorithm overlooks because both E and J have been visited. So it comes back to E, and then it comes back to A. But, I mean, it comes back to I, and then it comes back to E. But there is an edge that was not explored, but there are edges that have been completely explored by DFS. Pervez, could you explain what you mean by a mix? Are you talking about mixture of edges, or mixture of, are you talking about the time complexity? You mean directed and undirected edges mix? Yes. Yes, you can. That, and that should not be an issue representing, right? We just can represent both direct and undirected edges in a matrix or a list.